Hello everyone, July the 4th. Alright, let's do this. So we're gonna try this, and then we have to go for this one. Alright, what's this one? Longest subarray of ones after deleting one element. Given a binary array, nums, you should delete one element from it. Return the size of the longest non-empty subarray containing only ones in the resulting array. Return 0 if no such subarray exists. Well, the only chance that you won't have any left is if it's all 0. Right? Oh, well, no. If nums is only 1, length is 1, and that value is a 1, then it becomes 0. Okay? So we want the longest, right? Which means if we can have the count of everybody, how many ones, how many zeros, how many ones, how many zeros, if we have these counts, okay? If we have these counts, then we can just find the 1 zeros. And if we have 1 0, then we can always combine the ones on both sides. That can produce probably a longer one. So yeah, that shall do, right? So given anything, 0 1 1 1 1 0 1 1 0 1, right? Given this, we turn this into 0 of 1 count, 1 3 count, 0 1 count, 1 2 counts, 0 1 count, and a 1 1 count, right? So we turn this into this, then we go then one by one. The ones in the front doesn't really matter, so we just go through that, and then boom, we should record 3. Length is 3, and boom, this is length is 1. So we can delete that. So we add the 1, the 2 on both sides. So now we have 5. So we pick 5, and then this is 2. We take it in, and this we can delete. So when I have 3, so the answer will be 5. Yeah, I think that shall do. No DP is necessary. All right, let's just code it up. All right, I believe it's a group by. So we can say group by nums for kg in this count counts equals this. What's this? Is k and len list g. Okay. Then we say rest equal to 0 for k l in counts. If k is equal to 1, rest equals to maximum rest and L. Elif, oh, I need index as well. Elif 0 smaller than I smaller than len counts minus 1, because at the end it doesn't really matter that much. So if k is equal to 1, so elif I is this, and L is equal to 1. That's when we can delete, right? You can delete. When you delete, you can move the ones on both sides together. So that's why L has to be 1. If L is larger than 1, you cannot move the ones on both sides together. Make sense? Yeah, it makes sense. So when that happens, Aleph, what do? Well, when that happens, you can say res shall equal to maximum counts I minus 1 1 plus counts I plus 1 1 and res. When we're done, we'll return res. Okay, we'll put this up for a shot. We should probably test a little bit more. 3, 5, 3, 3, 5. Oh! That was unexpected. Huh. You have to delete one. Okay, so what we need to do is to see if anyone's deleted. Good test case. I don't even know. Has delete. Right, I left this, and then we say has delete equals true. Turn res if has delete, else res minus. Do res minus 1? What if it's all 0? Well, if it's all 0, then I'll have this. Oh, these edge cases. These edge cases. If we has delete or not res, right? That means we don't have anything anyway. Otherwise, oh, what if it's on the edge? Oh gosh. Oh gosh. All right. All right. Hold on. Else, if we have a 0, then has delete equals to true. And if this, then we do this. So as long as we have a 0, we'll delete it. Right? If there's no 0, so we don't have to check this. If there's no 0, everybody is 1, then we have to do this. Okay, update it. Yeah, we probably should throw in a 1, a 0, 0, 0, probably a 0. Try this. Looks about right. Looks about right. What is this? We group, right? All the consecutive ones and the zeros together and count them. Then iterate through each group and count. If we find a group of 0 and of length 1, we can delete that 0 and combine the groups of 1s on both sides. The tricky case is when we don't have any single zeros to delete. right? Thus, we need to set up a flag to indicate whether delete has happened. This also helps when there is no zeros in the nums, in which case we must delete 1, 1. All right. Solution sliding window. Zero count longest window. Zero count. So we count 0. Well, 0 count larger than 1. Wait, what was it? In the current window, the 0 count is 2. Hence, we will shrink the window by 1 until the starting point, until the start pointer starts pointing to index 1. Okay, so we will keep moving forward. Okay, if it's have 2 zeros, then you shrink 1 and then keep moving. And with 2 zeros, we'll keep shrinking until we get only 1 0. Then we keep expanding. I think that's what it means. As long as you have more than 1 0, we just have to give up, have to keep moving the start forward. So you have the start, okay? If it's 1, just keep moving. If it's 1 0, you keep moving. If it's 2 0, then you shrink. You keep moving forward, and it's 1 0, you keep moving, keep moving, keep moving. Become 2 zeros, you shrink. Keep moving 1 1 1 1. 2 zeros. Whenever you hit 2 zeros, then you have to shrink. But every time you hit 2 zeros, right? We assume every time you hit 2 zeros, it must be 1 at the back and then 1 at the front. And everybody inside shall be all ones or 1 0. Right? So I start front, you go, 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 boom, 1 0. I have 1 0, so I keep going until I hit another 0. Then I have to shrink. Right? Shrink 1. If it's keep shrinking until you have only 1 0 in the system. So we make sure that in the window we have at most 1 0. Right? At most 1 0. And if it's 1 0, we just keep going. Is it 1 0? Keep going. Is it 1 0? Keep going. When we have 2 zeros, okay? When we have 2 zeros, then we need to shrink. I think that's what it means. 0 count, longest window. Start from here. We count 0. If count is larger than 1, we will shrink. Yeah. And every time after we shrink, to become only 1 0. Okay? After we shrink, become 1 0, then we will compute. And I minus start, because we have to remove 1 in this window. Ah, it's pretty good. Sliding window. Got you. This is the sliding window solution from the official solution. The ideal is to find the longest window such that there is no more than 1 zeros inside the window, right? And the answer is the longest such window minus 1. We must minus 1 because 1 element must be removed. Okay, so SON. So with that, let's try. A result could be 0. Then we have a low is 0, right? And then 0 count is 0. Okay, I'll probably have to do this. 0 count. Okay. For high in range line num, just go all the way to the end. Okay. We say 0 count plus equal to nums high is equal to 0, right? If while 0 count is larger than 1, then we shrink, because there's too much 0, we have to shrink on the left hand side. Then we say low plus equal 1. And 0 count minus equal to int nums low is equal to 0. Boom, boom, boom. Once we get out, we know the current. Now the current window has at most 1, 0. So now we say res equal to maximum res and high minus low. Well, it should be high minus low minus 1, right? Oh no, plus 1. That's the total number of elements in the window. But we also have to minus 1, so we have to do this. So it'll be this, and then we'll return rest when we're done. Okay, let's run this. Ooh. Oh. Order is wrong. My bad. Order is wrong. Doesn't matter the time. Okay, that's that. Let's move on. Make array empty. You are given an integer in nums containing distinct numbers, and you can perform the following operations until the array is empty. Okay, if the first element has the smallest value, remove it. Otherwise, put the first element at the end of the array. Return an integer denoting the number of operations take to make numbers empty. Okay, so if the first one is the smallest, so we remove it. First one, it's not the smallest. We'll put it at the end. Okay, so we put 3 at the end. Now 4 at the front. It's not, because smallest minus 1, so we put 4. Okay, now minus 1 is the smallest, so we remove it. 3 is the smallest, we remove it. 4 is the smallest, we remove it. So we take 5 steps. Okay, so in here, remove 1, so 1 step, 2 step, 3 step, 4 step, 5 step. Gotcha. 1, 2, 3. Gotcha. All right. Looks not complicated, but so basically we have, you know, a bunch of values, and we have the minimum, right? Then whatever these has to be moved here, right? Has to be moved here. This one has to move here. This one has to be moved here, right? And then we have the minimum, so we remove it. Now we need to know the second smallest. Huh. Okay, let's say we have a second smallest, wherever they are. And then we need to know the ones in front, so they had to go back. And every single time, even if we know its position, right, we know its position, then everybody at the front need to move back. Okay, everyone in front has to move back. And then we find a new one. So every time we get the smallest value and we move everyone back, we can be just like the index, right? We can maybe change their index so they go to the back, and we got the new one, new smallest. We know their location. Do we know their location? We do. We know their location, and we know who is the front. So we know which ones need to be removed. So all these will be add a value. But once that is done, the next one, we know its position. We know where the front is. But then we have to update the value. And that can be O(n) squared. Even if we're not really moving, we're just changing the indices. Because we find one, we have to change everybody in front of it. We find one, we have to change everybody in front of it. Okay. Doesn't that feel like a binary index tree? It basically says we find an index, right? We find an index, and then everybody in front of it, everybody that's smaller than that, need to add a certain value. Well, binary index tree is we find something and everything larger than it, well, increment the same value. Not really exactly the same. Hold on, let me think. If we have 3, 4, minus 1. We know this is a small, this should be the first one to be removed, and so these two, so we know we take 2 steps, or we take 3 steps to pop this. And after we pop this, the thing is, we have something in the front, now we have the min, we have something at the back. Can we say, can we just divide it into 2, into this half and this half? Like, but so I take this many steps, plus the length of this plus this, so the length of the whole thing, to remove that. It has to remove over this half, move to the back, so the whole thing becomes this, right? This half moved there. Then, if we have something new, if the minimum is here, then this front half have to go to the end. Have to go to the end. And what does this mean, go to the end? Well, go to the end means we have a range, right? We have a range, and everybody in the range need to add some value. everybody in the range need to add a value. What's the value? Well, the value is, if this is 0, this is certain things. If we start from here, so basically the length of this, right? The length of this, add to this. So it's adding the same one. So you're telling me that we have a range, and this range had to add some value, okay? And there's a new value, okay? And then I'm thinking about segment sum, lazy segment tree. What I'm thinking is we can sort the whole thing to find their indices. Not indices, to find where they are, right? Where they are. To know which one needs to be the current smallest, right? The current smallest. Can they be equal? Yeah. Oh, all the values are distinct. Okay. All the values are distinct. So we can have an order to know which one goes first. So we can sort this, okay, with their indices. So we know. So now the first one is -1 at position 3. So we know this one is going to be the first one to be done. And now we can say the range, actually not position 2, range from 2 to 1 need to add the length of this. Length is 1, right? So we add length 1. Ooh, do we add length 1? No, we don't even add length 1. We add 0. We add length 0 because we delete this. So we add length 0, which is this whole length -1. So that becomes 0, 1 again. It doesn't matter. That's the current value. That's the current value. Now the next one should be 3 at position 0. So we look at that and know its value. Okay? I know its value, which is the current position. And I need to know, when we do this, what is the front of the position? Well, in this case, when we do it, okay, the front of the position shall be this plus 1. Right, front of the position should be 3. In this case, I actually should. Right, this is to plus. So when you put 3 here, right? If we don't change on the position, if we put 3 here, 3 is 0, 1, 2, 3, right? Which is to add the total length of this. No. The total length. All right, we have to put this one here. So it's the total length of this. Whatever this position is, when we move to the and. So we get a new, so yeah, it should be 3. Right, this position should be 3. This position should be 4. But it doesn't matter. And then we record the new start is 3. Now we have 3, 4. Now we find 3 is at position 0. So you find, okay, this one is going to be the smallest. Okay. And then when this becomes the smallest, so anybody is in front, you need to move to the end. So we check the ones in the front. How do we check the ones in the front? Well, we have the front position is 3 and its position is 3. So we know there's nothing in the front. Okay, so what if your min is here in the middle? Right? What do we have? Right, 0, 1, 2, 3, 4, 5, 6, 7. What if this is the smallest? Okay, when this is the smallest, and everybody put it to the end, right? So this value will become 7, 8, 9. This is 4, 5, 6, 7. No, this should be 8, 9, and 10. Right? 8, 9, 10. And then this delete. So we know the front is equal to 4. Okay, so this one is gone. We know the front is 4. Now, let's say we have the smallest is in here. Yeah, what if the smallest is here? If the smallest is here, then we say is 4 in front. So we need to go 4, 5, 6, 7, 8. They need to move. But how much do we move? And it's gonna be this range, 4 to 7, and a 0. Ugh. Maybe, but it seems convoluted. Can we have an easier way? Yeah, because the way I say it's convoluted, because we can have this situation. We have something in the front and something at the back. So we cannot say from 4 to 8, because the segment tree will build based on the original indices. Right? Based on the original indices. And these will change. So after a while, you don't even know which one's which. Yeah, here, this, the front is 4. You don't know what 9 represents. You say this is the smallest. Okay. Because the front is 4. Yeah, when the front is 4, we know the back. So we know this one. But these need all to add. Oof. Can we think of something else? Something else. We find the smallest. I already have more. So we find the smallest, right? And everybody in the front need to move. That's all fine. And then when they move to the back, they connect it with new things. Move to the back. Okay, they move to the back. Then what? Then I find a new smallest. Okay. Then how do I know its position? plus, plus. Okay, we have to plus that, because here we plus 7, plus 8, right? So I know this is position 9. So therefore, when we remove this one, now when we remove this one, we know the front has to take 9 minus 4 is 5 steps. 1, 2, 3, 4, 5 steps to put in the back again. And when we do that, we know the current addition is going to be 8 plus 5 is 13. And we can record the front right now. It's going to be 10. Right? 10. I am thinking about a solution of using linked list. Look, if I have 3, 4, minus 1, okay? And we sort the whole thing, and we sort the whole thing, we go through the whole thing, and then we record the address. All right, I'll record the address. So record. Yeah, we will record the address. So we do this, okay, and then we record the address. Okay, 3 is some ID, 4 is some ID, minus 1 is some ID. We sort this thing, so we get the sorted is minus 1, 3, 4. Okay, now look minus 1. We know, okay, that's the ID here. Then I delete this. Okay, and then, well, we can actually do exactly what this one is saying. We will cut the front. So we get the front. We actually have a dummy. Okay, dummy point to, so this is the head. So we will cut the head and have this pointing to the end. So I will cut this pointing here. All right, 3 and 4. That's 01. And we delete this. Okay, that's it, right? That's the operation. And then we can say the next is this, so we can find it. So this is all good. All we need to solve right now is the number of nodes at the front, because that allows us to know how many steps we have to do. Now to do that, for each node, we're going to have more than its value. We're going to have its position. So at the beginning, this position is 0, this position is 1, this position is 2. Now when we cut here, and then we know the head position, we can actually say the head position, right? The head position is going to be 0 at the beginning. Okay, and once we have head position is 0, and then now there's 2, then we know the number of steps to take to move is going to be 2 minus the head. So we have 2 steps, and then we do 01 to move here. Once we do that, now we're going to delete this, and we're going to say when we move, so we're going to say the delta, right? The delta is going to be at the beginning, the delta is going to be the length, so delta is 3. So boom, they move here, we set delta as 3. That's the initial delta. Okay, so now we know when we calculate this have to be plus 3. Okay, and we boom change this. Now we know the length becomes 2. So delta is 3, length is 2, and your start, your new head position. Your new head position shall be this the next plus delta. So new head position. So it's first round. Second round, head position is going to be 3. Okay? and delta is going to be the previous length, should be 2. Okay. Now we find 3, so 3 is here. Okay. So we will move the things ahead. So head position is the same. So head position, I'm here, right? So head position will be this towards this. And we will check. If they are the same, that means there's nothing. So we don't move anything, right? Okay, so if we need to move something, so if I have some elements here, then they will be moved to the bottom, to the end. Okay? And now the delta is 2, but it's okay. We don't have to worry about the delta at the moment. Oh, we do have to worry about the delta. Actually, we have to have current length. Hold on. We're almost there. I think this length has to be 3. And when we move down, the length now is 2. Right? Delta is 3. That's the previous one. Right, we carry on. When we move to the end, now the delta has to be 3 plus 2. Delta will be 5. Delta will be 5. Right? We move to the end, delta will be 5. And then we'll remove this. Okay. Then we'll look at the head position. So we have this, whatever its value is initially, it's going to add the delta. Add the delta. Oh, add the delta. That's not right. That's not right. You should add the previous delta. Yeah, we find this, okay. And then it's next. I have some value, right, as its next. And that value, we can add the delta at that time to produce the new head position for the next round, right? A new head position for the next round. And then what? And then we will wait, hold. Okay, we find the smallest one, okay? And we also know the head position. So the smallest position, that position will add the current delta. So for that, we know how many need to move. We add to the thing, and then we move the whole thing. Okay. Once we've done that, we will also find the new head position, which is its next. Right? That's next. Find its new head position, but how do you know the new next position shall be the old delta or the new delta? It's a good question. But it doesn't matter, because if we move, the head position will definitely just be +1, right? Whatever I am, I have my head position, right? I have my head position. And then somebody move to the end. Perfect. Then I'll just add 1. So that's the new head position. Yeah, that's the new head position. So I have the head position. And then we find a new thing. Okay? But what is this new smallest? What is its head position? Oh, it depends. Its head position its position can be previous delta or the new delta. Dang it. The previous delta or the new delta. Now all I know is some node is going to be the smallest, but we don't know where it is in this entire linked list. We don't. Okay, so we don't know if the new things is in the front or is at the back after we move this, right? After we move. A move is easy, but we don't know where it is. I feel like linked list shall work, but I don't know the... Yeah, this is something I don't know. I know the head position, that's good. I can do the movement in O1, that's all good. The only bad thing that I don't know is the new position after we move the front to the end. Because I don't know if the new value is in the front part or is in the back part. That's something I don't know. That is something I don't know. Exactly. That's something I don't know. But what I do know is only the values in the front. You need to add the delta. Okay. But the value... do we have some other ideas? What other trick can you do for linked list, right? If you have a linked list, we already know. The only thing is when I get this ID, I want to know its current position. That's it. If I know its current position, I can solve this problem. Then how do I know the current position after we make a move, right? Well, when you make a move, you need to add a delta, right? So for some linked list, you need to add a delta. For another linked list, you need to add a different delta. Yeah, that's it. The deltas can be different. It's very individual. It's attached to every single one. But I don't want to go through every single one. That's the whole point. The whole point of doing linked lists is we don't have to attach to each individual ones. Then how do you know? That's why it feels like segment tree, because on a lazy segment tree, we can add the same value to a range of elements. But the problem for the segment tree is the segment itself is changing, right? The segment itself is changing. I can have these values at the front, and then I can break them up, so they'll be grouped with somebody else. So that is changing. So a lot of things is moving around, which makes segment tree also not ideal. What else? What else can you think? Well, can we analyze it? So we have a smallest, okay, second smallest, okay, and a third smallest, fourth smallest, right? We have a in order. If I know like the nth smallest, and then it will make some changes, can I solve the n+1 smallest? Maybe we can DP it. If I know the nth smallest, okay, so I have something minimum, something. If I know this is the, let's say, nth smallest, okay, and then to remove that, we'll do so many steps, right? That's fine, totally fine, we know. So once this is done, can we know the n+1 smallest? Well, we will know where it is. Well, the thing is that the shape also changes, right? Because this one put in the back, and if the next one's here on this half, or the next one is here on this half, the result is different. Actually, not really that different. Huh. I mean, if the next smallest is here, then we know these two need to move. So these two need to add. Like in this range, they have to add. Okay. And if the smallest is here, right, then we know this range need to add because only this will do. So if my smallest is here, right, I say, okay, range from this to this will add. Perfect. But next, if the smallest is here, yeah, that's the thing because you put down here. So next smallest here, then the range to add is going to be this and everything here because you move these three to here, all right? So you have all these range. So you have a range on the left hand side and a range on the right hand side. And after a few rounds, and you get confused. Oh, it doesn't feel like the way to go. Doesn't feel the way to go. What else? I don't know. Let's take a look at the hints. Segment tree. Oof. The order in which the indices are removed from there. I know that. We can do that. Only the array lengths matter. That is true. That is the array length. Because we just need to add the value so we know what the positions there will be. Right? I just need to add. But yeah, my thing is just if you have here, then you got some on the left, and you have to do everything on the right. Okay? You need to add. Yeah, let's say you do that. You do that. You move this, and boom, this thing comes to here. So everything in front, you say these gets you add a new position. Okay, we have these as new positions. Okay, that's fine. Now this is the smallest, right? This is the smallest. So everything to the left of this, anything that's smaller than this, right? Anything that's smaller than this. How do you know what is smaller than this? Well, if you're a segment tree, what are you querying? A query So you move these to the other side, okay? Hold on, you move these to the other side, right? You move these three to this side. And then we say this is the front, okay? Then we have a smallest. New min is here. Then who needs to move? Move just means which segment need to add the current length. Well, we have, what is it to the left of this? And whatever are these? Let's keep looking. Only the array length matters. Yeah. Upon removing an index, decide how many steps it takes to move to the next one. Yeah, we know that. The number of steps taken is basically the length, right, added. I think this is pointing us to segment tree, but I have trouble figuring out how the length is added to each value. Right, we have this, and then we have the current. Okay, but we cannot say to the left because there's no more left and right. We just have its, let's say, its position. Okay, we have its position, and everything that's smaller than this position. So can we do a query? Can we do a query? What do we do query in segment tree? Well, we query, a range. That's what we query in segment tree. We query a range. Because in this case, we don't have really a range. I want to know the range. I want to know a range such that its value is smaller than something else. And I want to increment that range. And that range could be broken up into several smaller pieces. That's why I feel that's not the right way of thinking. All right, I have to spend more time on this. Let's call it for today. Yeah, I gotta think more. All right, I'll see you guys tomorrow. Adios.